Hi, people. We're continuing with our notes and the review of life science and cell biology in a nutshell. So we are studying currently actin filaments, and we just did microtubules. These are uh, well, they're part of the cell that control its shape and its integrity. So, with the increased and decreased volume of the cell due to water and water entering and exiting the cell due to different concentration gradients, these two parts of the cell change in their orientation as they control the protoplast. So, that is the internal part of the cell. So we were learning about actin. So let's see. So it was talking about that there's a thing called calcium signaling associated with the way the cell changes its shape. Also, it says it remains to be clarified if calcium mobilization triggers actin filament formation directly by the increased polymerization of actin. So calcium has something to do with the way actin changes its orientation and shape within the cell through a calcium signaling cascade. Oh, and Ruben's helping me read notes. Say hi.
Oh.
Here, read this one.
Actin microfilaments were able to recognize rapidly in order to reorganize. Can you see that? Rapidly in order to accommodate the shrinking protoplast during plasmolysis.
Protoplast is the internal cell, which consists of the cytoplasm and all its organelles inside.
The actin filaments radiating from the nuclear surface were still visible in plasmolysis cells. White cortical actin lined the plasma membrane and stretched out towards the cell wall in Hechtian strands.
That's just what the actin filaments are called.
Endoplasmic actin was presented in transvacuolar cytoplasmic strands that traversed the vacuole, thereby connecting the nuclear cytoplasm to the thin cortical cytoplasmic layer immediately below the plasma membrane. Since the subcortical cytoplasm was highly dynamic and organelles
therein are constantly streaming in interface cells. So, and actin microfilaments help with the movement of the cytoplasm and the organelles. And this diagram shows that these actin filaments are glowing green in these cells. So it says here, where are we? So that's the section of that. Okay, so I have a little more details about the difference between microfilaments and microtubules. Ruben, can you read this for me, please? Thank you. So
microfilaments and microtubules are key components of the
Cytoskeleton.
cytoskeleton and eukaryotic cells. A cytoskeleton provides structure to the cell and connects to every part of the cell membrane and every organelle. Microtubules and microfilaments together allow the cell to hold its shape and move itself and its organelles.
Thank you, Ruben. This is showing a stained sample of the microtubules and the microfilaments inside cells. It looks beautiful. Okay, can keep going.
Microtubules are hollow, rigid, uh, cylindrical tubes composed of tubulin
Units.
subunits. Microfilaments are solid, thinner structures composed of actin subunits. Intermediate filaments are, though, tough rope-like fibers composed of a variety of related proteins like keratin.
So the picture here showing it's showing microtubules and the subunits. So obviously it's much wider, each cylindrical subunit. Intermediate filaments are thinner, and so they're measured in nanometers, which is a very tiny measurement unit, and microfilaments, so it's in like millionths of a meter, and then microfilaments are more on the exterior of the cell. Intermediate. Oh, okay. Intermediate. Okay, so there's actually like 3 kinds. Okay, so those are the major kinds of filaments, and then so cytoskeleton, microtubules, alpha and beta tubulin of equal polarity with 3D structure from heterodimers, meaning they have multiple subunits, non-covalently bonding into linear array with alpha tubulin at negative, beta tubulin at positive. Alpha end is growing slower than beta end, forming sheets which curl up into tubules. So that's the way the microtubules look like, made out of little tiny units of alpha and beta tubulin. Correct. So it says there's 13 units of tubulin per helical turn. And then the actin filaments, as part of the cytoskeleton, are made out of a G-actin monomer, and they use ATP and magnesium in order to function and to move around. Actin monomer gaps align toward the negative end of the filament, spiraling along the long axis, 13 monomer units per full helical turn, just like with the microtubules, going faster at the positive end. So they're a bit different. And then myosin, these might be, so they're different kind, also in filaments. That's the structure. It says bipolar thick myosin filament in muscle cells are shown, Muscle cells called the sarcomere. And it says there are 70 different genes coding for various intermediate filament proteins. However, different kinds of intermediate filaments share basic characteristics. In general, they are all polymers that measure between 9 and 11 nanometers in diameter when fully assembled. So we're going to go over this chart I have with comparison of a little more detail about microtubules and microfilaments in our next video. Thank you guys. Bye. Say bye.
Bye.